Welcome to the 30-minute case study webinar series. This is John Sankey. I'm an engineer for True Blue Technologies. It's a sales engineering firm that represents or facilitates Aestus, Tersus Environmental, TRS Group, and West Bay Instruments Technologies. This series of presentations focus on the main topic of managing complex sites with high-resolution site characterization and then focused remediation. Today, we are super pleased to have Dr. Todd Hallahan discuss how an ultra-high resolution site characterization conceptual site model update helped save approximately $4 million at a NAPL sediment site. So Todd is a professor and the Sun Chair of Hydrogeology at Oklahoma State University and serves as the Chief Technical Officer for Aestus. As one of the recent NGWA McElhaney lecturers, Todd gave talks all over the world. So thank you, Todd, for presenting this case study today. You now have the lead.
Thanks, John. And the case study today I'm going to be presenting with Jeff Gentry. He's an engineer that's a senior expert for Jacobs, and he's worked with us on and off on different projects for about 10 years now. So he's got some feel for the technology and how it's applied. So we're going to get some input from him on this case. And then I also need to tell you that as a person who's a professor and a chief technical officer at the same time, I have a managed conflict of interest where I have students and I have employees, and I have to manage both of those in an ethical way. So if you got questions about how that works, just let me know. So we want to be respectful of your time. That's why we do these as 30 minutes. And we asked people earlier this year, you know, is an hour good or 30 minutes things, and people tended to want to do 30 minutes, so we're going to try to fit in there. You're welcome to stick around as long as you like and ask questions, or get us back on the horn later on to chat about technical details or things like that. So feel free to stick around, but we're trying to make sure that we respect your time. This is being recorded, so if you need to be able to look at it later, you can get a copy of that. And then CEU certificates are available for the webinar if you need those for your certifications. There'll be a giveaway for an Amazon card or Starbucks card, depending what kind of thing you want. That gets drawn later today and you get notified. You can submit questions to increase your chances. And if you have a minimized toolbar, the little orange arrow gets you more of the tools where you can see where to submit your questions and things like that. And the winner will be notified next end of the week, I guess, be tomorrow. So next step. So looking at NAPL discharging into sediments, it's similar to any other NAPL site, except you have real access issues. So in terms of that, you still want to know the distribution of volume impacts, but the cost per volume has gone way up. And so anything that you can do to reduce that's a good idea. And then trying to understand the paths, they're probably not horizontal on these kinds of sites. So as you come into waterways, basic hydro says you probably have some vertical flow lines. And so thinking about how they're coming in will affect what kinds of remediation you want to do. And then when we start looking at these things electrically, and we've done a few of these things around the world, we find that the habitat for them is really important because every one we've looked at so far has been bioactive. And so thinking about the habitat of where they're growing and why, the bioactivity ends up being pretty important on these sites. So it's something to always keep in the back of your mind if you're thinking about these things. Electrical looks conductive when you have a lot of bacteria around, and it ends up being key on a lot of these sites. So I'm turning that over to Jeff to tell us about how he ended up in this site and dealing with it, and then bringing us on to help with the conceptual site model. So Jeff.
Thank you, Todd. Yes, I'm Jeff Gentry. I'm a senior expert with Jacobs. Prior to that was CH2M Hill for a total of about 33 years. So I've been around a while. I got involved in this site for a private client back in about 2005 when releases were observed during a low lake level period of Lake Michigan. We did some work to measure the impacts. We did a lot of interim measures to really mitigate the current release. And really we went through the usual, 5-year or more remedial alternative RI with the state of Michigan, and really came to about 2015 where we wanted to really put the final remedy in. And really what this remedy did is we really wanted a passive only remedy to control the NAPL migration, get the NAPL out of the lake, and also reduce groundwater discharges to where we can meet the compliance standards of the state of Michigan, which at the time I think were 11 micrograms per liter of naphthalene. Next slide. So we did a lot of work to characterize where it was in the dissolved phase impacts and NAPL impacts within the upland and all that, and the sand flat. What we really found in our NAPL site conceptual model was what I see a lot with kind of neutrally buoyant NAPL. Creosote can be a little downward moving, but not always. That it never really made it to the aquitard here upland, because that's because we had so much groundwater and other low permeable lenses holding it up. But when we got to the lake, all those real hydro forces go away and everything sunk on us. We were able to address, have an agreement with the regulators to address the surface impacts here and keep them and the subsurface impacts to remain. Back to you, I think, Todd, on how we brought Aestus into it.
So they brought us on because they knew this is going to be expensive to deal with. You're dealing with out in the lake and trying to deal with those issues, and you wanted to be able to get some control. So what electrical hydrogeology does is says, okay, well, we want to fill in the domain between our point data. And you eventually figure out you can't poke enough holes to look in the world in 3D if you're going to try to do it in some cost-effective manner. So electrically, we can look down and get a pattern, and this is basically a well log, except for it's 112 of them tied together into a picture. And so we can get to data densities, and this is a little Karst gas station site in Missouri, and we can take those high density images and pile them together, and you'll have a site conceptual model that's like 10 to 100,000 data points on a typical model. And what that allows you to do is look around the site and be able to understand the patterns you're dealing with. So when you go in a sample, you're doing that a lot more precisely. And then when you want to figure out what volume you need to deal with, you understand the constraints of that domain much better. But as I mentioned, we got to think about microbes, and conceptually, while I think about microbes in the subsurface, as a person who's not a biologist, who doesn't have a warm and fuzzy for all these things, I think of more of an engineering perspective. It's the mold growing on the cheese and out in the back of the fridge. So your cheese is the NAPL, and then the mold grows where it wants to grow. And there's a nice quote from Harvard Law that even if you're in the lab, they're going to do as they damn well please. So we see that in the subsurface as well in our data sets, is that they'll grow where they're happy. So on colder sites, like somewhere in the north, a lot of times they'll grow up underneath the NAPL where they got a little bit more warmth, but their pattern is built on where they're happy, not where you want to predict them necessarily. So it's a bit tricky. Your NAPL that's not degrading is like a nice fruitcake. There's some reason they don't want to go after it. And so you'll have NAPL that gets left behind that just sits there. And so we get these sites that are old, and we know we're somewhere between a really moldy chunk of NAPL and fruitcake sitting back in the uplands. And we got to figure out what we're looking at. And electrically, you're looking at very conductive portions where there's a lot of bioactivity, and very electrically resistive portions where you have NAPL phases that aren't being degraded. Taking the picture over water, you don't have to fit a drill rig. So we just need to connect electrodes to the surface of the earth. So when you do that, if you got like a channel or something, you can stretch the cable across there, connect to the water, and use boats, and you make sure people are working safely, but you just have to touch the water. And so the picture at the right there shows the electrode. And so once you touch the water, you've made an electrical connection, and you're not using amounts of current that are going to kill fish or do interesting things. You're just taking pictures electrically. So it doesn't matter that you're over the water and you don't have any hazards associated with that. But if you're in kind of mucky stuff like the center picture, we'll typically put stakes in the ground just to hold the electrodes in place nicely and make sure that they're well connected. And if we're floating, we'll use a linear flotation device that other people will call a pool noodle. But it works really well to go take those pictures and get us places that drill rigs just can't go. Process-wise, the pictures don't tell you everything. The pictures are similar to having an X-ray. You see that something looks funny, or you get an MRI and you see his liver doesn't look so good. So you go through this process where you put all the information from the site in a 3D model. You scan and add those data sets, and then you come up with what do you think the patient's doing, and you work through that and decide where to do confirmation drilling. And you biopsy the tumors, check those things, and that's when you get to a conceptual site model that you've got 10,000, 100,000 data points, but you've got the point data you need to make the decisions on a biochemical basis. So conceptually, when we start working out how these things function, we start out with sort of mysterious stuff. And so I think about Dr. Pimple Popper, if you've ever watched her. She gets people to come to our office and they've got weird things on their skin and they got to figure it out. That's seep or ebullition area. So Jeff comes to me and says, I've got this weird thing in the lake and I need to figure out how that all connects. So as we've done those things, we figured out on all the cases we looked at so far, it's an electrically conductive feature. So it's basically a discharge of infection. And we normally think about bioactivity as great, they're break it down stuff, but when we think about it coming out into water body, we're like, oh, not so good. But as far as we can tell from the sites we've worked on, it looks like they're causing it. So one of the things I've asked people previously is, can we kill them and make them not have stuff flow out there? And the best I've come up with is that you can maybe plug it up by having them get more active and cause biofouling, where they slow down their own flow because they're too active. So if we look at that in profile, this conceptual model is that the source is there, and we've got to think about vertical things and what happens vertically when you get these things going near a water body. But that path is going to be some sort of bioactivity, and it may have some biosurfactants helping it out. But that source is probably going to be not particularly mobile, except for the infection that it has. Thus far, that's been reasonably true in terms of the data sets we've had for all the ones we've looked at. So we're typically looking for a conductor and some bioactivity bringing stuff out to the water. So if we look at the data sets out in the uplands, these are the resistive portions above 150 ohmmeters in the orange. And then the red line is the boundary of NAPL that was delineated for the site. And you can see that these patches of NAPL remain left behind, and you can go in and biopsy these tumors. And what we found is you've got a couple of remnant sources, and you got we think it was an old log chute that they were sending it down to the water. So we find those features and we can look at what would need to be cleaned up or what needs to be targeted. And that helps a lot in the uplands. And then if we look in the water body, now we're going to look at a map view slice of the data. And so we slice through that data about 5 feet down. So we're basically in that surface expression of that NAPL in the sediments. And lo and behold, that little nose on the NAPL that heads out to the east, we're looking at something that is bioactive in terms of the electrical data. And so it looks like the NAPL's sitting up there and it's going out and getting bioactive and heading out into the waterway and dragging the NAPL with it. And so that's ended up, this is one of our earliest sites looking at this problem, but over time, all of our other sites look very similar, is that when you get to that spot, you're looking at something bioactive. But in this case, you're looking at a colder terrain, and so the bio doesn't just stop when it gets back towards the shore. You got to think about the flow line direction and how they're going to want to grow and be happy. So the purple in that case, if we drop down another 5 feet, 10 feet, we're going to go down to 15 feet down. You can see the infection is up under one side of it, and we can think about how that infection has grown and what it's doing. But we don't have great farming techniques for how to control infections or try to steer them a lot. So, that's sort of the future where we go with understanding bioactivity in the subsurface better, is we can now start seeing that with this method where things are infected, but doing more control factors. We still need to work on that a bit. And I'll turn it back to Jeff to talk about how we use that information.
Yeah, and what we really did is we did a couple of things here. We knew we could get some of the NAPL out of the surface, so we were always planning to do a surface restoration, and that's kind of the shaded area that you see out on one side. We knew that we wanted to control the surface NAPL and other discharges, but we really don't want to block all the groundwater and pump and treat or divert it all around. So what we did is we put a shoreline barrier in with some recovery wells behind it to get maybe some of that deeper NAPL out. But we left windows in it because we wanted the groundwater to discharge. And then what we did is we kind of encompassed the entire upland with a slurry wall. And that was no easy feat. But what we're trying to do is block off all the groundwater discharge so that we really make it just where the local precipitation kind of is the recharge of the area. So what we did is we went into some groundwater modeling exercises that are shown in the results, and you were combining this with the results of afterwards. And so let me go through what the process of this. The brown lines you see there are the original contours of naphthalene coming out in orders of magnitude. And we could see that even under current conditions, we had a good degradation of the materials as it went out. What we did is we kind of figured out what the groundwater travel time was with that. And we used that as a surrogate to project what the travel time looked like with the remedy. And that's what you see in the blue are the travel times. We're kind of like blocking the groundwater around. It's kind of leaking out under the windows. And it's kind of going into the low pressure area, downgrading of the wall. But what the Aestus data showed is like, well, is that degradation going to occur? So if this was overlaid on what we showed as that conductive pathway, it was really the overabundance of the conductive pathway that we had biodegradation already that kind of gave us some good confidence that this biodegradation would occur. So we dug out the NAPL, we put a cap down 5 feet below it, we've sampled it in 2015, and we kind of let the dissolve phase attenuate here. And the data since then has supported that the results are as predicted. We do see compliant groundwater, pore water above the cap. We have effectively blocked that off. We do get naphthalene discharge. So this is some pretty early data. It is improving as the site attenuates. But we do get this little halo out there thing that we're still working with the regulators with. And I always make the analogy that the size of that discharge area out there is about the same size as a treatment plant would be if I was pumping and treating all this groundwater. But we're just letting that bioactivity that was identified in the Aestus survey be our treatment. So these are the pictures before, after, and after the completed project. I mean, we're pretty happy with this remedy because of its sustainability. We are not pumping and treating groundwater. I mean, at someday maybe that will become a requirement, but we don't see where the data supports that. We're still working with the agencies. And we have not seen NAPL or any the areas recovered well. And we're real happy from our end and the client end on so far the performance of the remedy. Back to you, Todd.
So in terms of doing these projects, hopefully you can kind of see in a quick version that you got to work together in terms of the folks doing the remedy and the folks doing the imaging and figuring out what you're working with and sampling it in a way that gets you to a regulatory endpoint. So you got to integrate all that stuff in a good teamwork between your imaging folks and your remediation folks. That's needed in order to get that ball moved forward in the most effective, efficient manner. But we got a preferential flow path identified and got lines of evidence to deal with where the impacts are at and where bioactivity is strongest, and the field data to help support the groundwater modeling results. So by getting rid of the groundwater pumping issue, you save about 90% in operation and maintenance. So you go down to about 30,000 a year from 300,000 a year. So that saves total to the client about $4 million. And being able to understand it so that you can be more predictive once your solution is in place, it really helps on the regulatory side because they know why you did certain things and they can see what the plan was and what you're trying to control and what's going on a bioactive basis as well as with the standard remedies. So for these kinds of sites, when we're dealing with sediments, we found, hey, it's all based on how much volume and depth you got to deal with. So if you've got multi-million-dollar remediation out there, you get a really strong return on investment to do scanning's about $100,000 thing, give or take. It's not a 10,000, it's not a million, it's kind of a $100,000 thing. But if you've got millions of dollars of sediment cost, you go, okay, well, let's take some pictures out there and understand what's really going on. For all of our sites so far that we've used this, bioactivity appears to control if you've got a seep or an ebullition area. Thus far, 100% of the time, it shows up as a strong conductor. And so it looks like it's the discharging infection of a site. And we're starting to understand how to manage that infection. And then looking at these, this is similar to most of our other sites. Depending on what your weathering state and what the NAPL is like, it could be a conductor or resistor, and it depends on that bioactivity. So in the future, we can think about as we understand the problem and its electrical structure and what's going on biochemically, we can then start thinking about what's the most optimal way to sample that to get to regulatory endpoints so that we're efficient and thorough with our analysis. But with bioactivity, they're a little bit funny, and so it's sometimes a little tricky to make sure we get all the things, and we're still learning about bioactivity relative to these imaging techniques. And it's called biogeophysics if you want to go look it up on the academic side. On looking at these sites, we can also throw a cable in at the coast or anywhere else you like, and you can have an electrical well that watches what's coming through, so that if you wanted to treat it by where the flux is highest, you can watch it where it's changing electrically and know that's where the flux is highest, and then go treat on the uplands area the biggest flux paths out to the water body to be a little more efficient. And we still need to improve, this was a conclusion from my last set of slides when we were talking about bioactivity, is we need to think about more like farming them. So not only getting them to grow, but what to do with the weeds. If they're making stuff go out in the water body, can we get those guys controlled so they don't send stuff out there? Because it looks like they're the ones aiding that flow path. And so while it's nice they're breaking stuff down, mobilizing stuff isn't a great side effect in a lot of these cases. So thinking about better control over them is something I think we're always going to be working on. So that's what we have for you, and open it up for questions that you might have for me or Jeff.
And again, you can click on the orange arrow to open up the tab to ask questions via the text. We do have a couple questions, Todd. One is, how deep of a water body can Aestus image through, as this site looked like it was fairly shallow?
So our image depth is 1/5 of the total line length. And so it's just how far down do you want to go? So if you want to look down through the ocean, you just need a longer piece of wire. So for our sites where we're floating electrodes, the water body is part of the upper part of the image. And then we go into the sediments part of the image and look down below that. But on those, we'll sometimes go half on land and half on water and extend it out so that you can see a cross section, or we'll set points or do a couple other options depending on your water depth and how much current you might have. And we try to be as, we try not to be too overly interesting of trying to manage waves and stuff. So we'll look for calm conditions and things, but the water depth doesn't matter, it's how long the line is. And so we would just make that part of the upper image if you're dealing with deeper water.
Okay, thanks. Another question is, maybe this one's for Jeff. How much money was spent on the interim remediation before Jacobs and Aestus teamed up?
Not what we did at that time is we spent about $250,000 and put in a 15-foot deep vertical permeable absorptive wall of organoclay right across the shoreline, and extended some reactive core mats onto the shoreline, which are an olefilic clay absorbent. We blocked the flow for 10 years. Let's see, we put it in 2005 for almost 10 years with it. It did show a few signs of breakthrough at the end. But that was a very cost-effective thing because it kept all the NAPL basically behind the wall. And we actually left the olefilic clay in the ground and put the sheet pile wall right in front of it. So it's actually kind of still working out there.
Thanks, Jeff. Easy question. Will this presentation be available for download? Yes, we're going to send out a follow-up email to everybody who's attending with a link so you can download and watch it again or forward it to a colleague or wherever you would like to do. Another question would be email. Todd, you mentioned Aestus can detect bioactivity. What's the mechanism behind that?
So there's a few. Originally, when they first started figuring out that bioactivity was conductive, they thought it was that they were looking at their waste products, that the waste products coming out were conductive materials, and so it was making these more conductive. But they actually make it too conductive for just being a little extra salt in the water. And so they found that the biofilms that they make and the slime they produce is about 1 ohmmeter. So that the body parts essentially are fairly conductive. So as they attach themselves to surfaces and connect up as a colony, they start making it more conductive, and you see it. Some of them have nanowires, so they actually have wires that they build. And so as they actually wire up the surface, they'll be like taking stuff and dropping electrons off at the other redox zone. And so not only do they have a structure locally around like a NAPL, they also get a structure based on the redox zones in the subsurface. And then some of them, especially like on DNAPL sites, they make an incredibly conductive signal that looks like you're looking at a metals mine. And that one, we're still uncertain about what you're looking at. And so there's still signals we got to understand, but they all tend to be conductive, except for when you get to methanogens. When you get to methanogens, if they produce enough methane, when we look at like old refineries, they'll make methane bubbles and you'll get gas traps. And so up under like a confining unit or something, you'll get a big resistor of the methane that's piling up. And what you'll see in a regular data set on that is they'll have boreholes around the refinery, and the log will say dry clay. And you're way below the water table, and you're like, so why is the clay dry and powdery? And usually it's charged with gas, and it's either off-gassing methane, or in a different situation might be off-gassing CO2. But we'll get these signals that you go, why is it so resistive? Is there a bunch of NAPL? And you go, well, there used to be, but now it's just the gas left behind. So now we're starting to target conductive and resistive signals on the bio side, because they can sometimes produce so much gas that they can actually make a resistor. But it's actually good news, because their tumor is just some methane and they don't have to do a lot of remediation or anything.
Thank you. Another question from Tom. It's kind of a two-part question, but it's all tied together. So do buried utilities, for instance, pipelines, affect the output and images generated from your probe data? That is, can you use the biogeophysics to map out an NAPL plume in a tank farm setting where there are numerous buried utility lines?
So in terms of that setting, we go through refineries and things all the time. And so we've got ways to look for if you did actually get something to show up in the data sets as a noise feature. The technique actually isn't great if you said, I want to find all the utilities. Most utilities aren't well coupled electrically to the subsurface. They're buried in gravel, or they've got a coating, or they've got both. And so a lot of things kind of disappear because it doesn't make a good electrical circuit. So you need something that's not too rusty, not coated, that shows up. And so there's different combinations where you get that. But going through refineries and things, what we find most times is that you get on old refineries, you get a conductive signal anyways, even if you're in you're in an area without pipes, and you just have so much bacteria growing under those areas. So on those kinds of settings, you can use it to map it out and then define areas where, yeah, we need to remediate this because we still got a bunch of stuff left behind, but these areas are so bioactive, and we can look at defining trends and looking at some other ways to define how efficient the bioactivity is being. But you can use it to mark off zones that you're just going to let bioactivity take care of the site, or where you need to add a little something. One of John's companies can help you out to feed them and make them happier. So it's looking at it from a biological perspective, which is a little strange relative to sort of inorganic evaluation we started out with in pump and treats and stuff, not thinking about groundwater as a living thing. But on these sites, it's basically that you're growing something, and is that helping or hurting your regulatory objectives?
Great, thanks. Another question is, have you seen a trend over time at these type of sites in terms of how NAPL migrates from upland to the water body?
A lot of the sites we get on this kind of problem are old, and what we see is that you've got NAPL. We got one of them that I think it was one of Jeff's sites, and you could sample the NAPL with a spoon because you couldn't get it to flow. And so you just get old, thick NAPLs, but you'll get a place where you either have a different source or it gets infected, and it just makes stuff start really cooking along. And so we would like to sort of perforate the heck out of one of these paths and really understand what the redox changes are and where the biosurfactants are being produced and all those sorts of things to get a better handle on that conceptual model. But overall, that's what we're seeing.
Yes, I do have a few sites where the NAPL seems to defy physics and still moves. I mean, I think the way I kind of look at this, that there's usually an event that creates a pathway that the NAPL moves by a head. But once that is established, you can get continued migration without, once you've cut off the head, just by some other ways the NAPL moves. So, you know, I think that the ASTM is coming out with some good guidance on sediment, mobility in sediment, methods, etc. It connects a little bit to the upland. So I just encourage people to look for those. I don't know if they came out yet, but I do believe they'll come out in the near future if they have not.
Okay. Last chance for any texted questions. I think we've answered all of them thus far. And again, there'll be a follow-up chance as well, because we'll send out follow-up email with the presentation link, and you can always email or call us any follow-up questions if you have them. We do have one more, just came in from Tom again. Are there limitations when there is a substantial accumulation, meaning NAPL thickness greater than 30 centimeters, in a groundwater well installed into sandy sediments of NAPL? In other words, if a monitor well is reflecting a lot of NAPL presence, are there any limitations, you know, relative to this condition?
So we've looked at sites with this technology with up to tens of feet of NAPL, and it's you're looking at a structure of that phase and how it's sitting there. So if it's a pure NAPL phase, a nice fresh spill, it's going to be resistive, and you're going to see a resistive structure. But what you see relative to the thickness is you're seeing what's actually out in the media. So if you said, I've got a sheen, or I've got an inch, or I've got a foot, when you look out into the aquifer, what we're seeing is where it's sitting in the pore space. So you might have we only have an inch in the well. You might have several feet out in the formation of where that distributed zone is. And then we'll have times where people say, I've got, 10 feet in my well, but we look out in the formation and it's not that extensive. It's just the capillary forces, the differences between the wells and the formation. You've got a picture of what's in the media, and you've got a well telling you a property of the physics of the fluids. So it's those combinations, but the thickness of NAPL, it's just part of the picture. And it's as if you're taking a picture of a different kind of rock. You're just looking at the fluid as an electrical chunk.
And we've done sites with a little bit of NAPL or a tremendous amount. So there's no limitation there relative to the use of this scanning technology. Tommy had another email question come in. It says, mention was made regarding contact with water. How would we conduct a survey in areas with organic mats similar to reeds or rushes?
In some of those situations, it depends. If there's enough water over the top of all that stuff, we don't have to actually go beneath them or do anything. If they're sitting up on top and they're dry, we need to somehow couple to something conductive. So if we can punch a stake through that spot or do something to get coupled to the earth, it just depends on what the setup is. And so if there's, hey, it's really dry, but we don't want to puncture our system, you'd wait till it was the wet season or something and do things like that. So it's coming up with, how do I couple to the earth in your situation? And we do this discussion for going through factory plant floors and going over waterways. And it's just best as looking at a map, looking at what I'm allowed and not allowed to do in terms of coupling, and then coming up with what's the solution. And we've engineered solutions to take pictures basically anywhere. It's just, how do we do it based on the context of the site?
Great, thank you. I think that's it for the questions. So Todd, I'll turn it back to you to close the meeting.
Okay, thanks. So thanks, folks. We'll have one of these again. I think, John, are we doing this again in a couple months? Every 2 months or something for electrical views?
We are indeed.
Okay, and then your you have another webinar series coming up for other technologies?
We have one for ZVI coming up, and then another one for deep multi-port monitoring. So I'll send those out to y'all.
And if you're not on John's list, just ping him with an email and he'll happy to sign you up, and you can get your CEUs and get more technology defined. But if you have any questions for us, our contact info is up there, and Thanks for participating. We really appreciate it, and always, hopefully, we make good use of your time.
Thanks.
Thanks,
Todd.
everybody. I'll close the meeting.
Thanks, Stuart. Thanks, Todd. Thanks, Jeff.
Yep. Thank you all. Have a great day.